Okay, let's get started on section 2. Totally transition to a new topic. Welcome back. I hope you're refreshed, bowl of coffee or tea or liquids and ready to jive again, right? So I know you guys are like jet lagged and all this fun stuff, so I'll try to run around and get you amped up like a game show, okay? MP, right? Like so. Okay, so section 2 is we're going to kind of a little bit build on making hopefully useful MPI information, as we'll say. These are virtual topologies where on, as we saw earlier, right, we had a Cartesian grid, for example, or an unstructured mesh. And maybe we want to inform the MPI implementation that, hey, we actually have a regular data structure that could be useful to the MPI library if the implementation, such as like OpenMPI, takes advantage of that, or a Blue Gene, for example, back in the day, could take advantage of useful information and reorder our MPI ranks to be more efficient, okay? So this next section is on Cartesian topologies, right? So Cartesian meshes are fairly limited. We're going to talk about graphs tomorrow, which is way more, right, like unstructured kind of data sets. But the principle of building a virtual topology, which we feed to MPI, is kind of the same, right? After we construct it, right? But so today is the more rudimentary one where we're going to build it for Cartesian grids. Now, it is real, and I have done it for real at a similar training program when I was a graduate student. And we'll see some of the results where I was actually able to like scale to 1 million ranks. And I was like blown away that we could actually use this stuff. This is like, I shouldn't say this on tape, but if you're like a person like, why isn't my clicker going? Okay, what is a structured mesh, right? So a structured mesh is simply a regular connectivity pattern where all the communications for every element is essentially the same, right? So in a Cartesian mesh, we know this element block is going to communicate with its nearest 4 neighbors, right? East, west, north, south. But this element over here, somewhere else in this mesh, in this structured regular mesh, has the same communication patterns, right? So here, in this example, they all have 4 neighbors they're going to communicate with. In this example, right, we have I guess these are 6-sided element types, a little bit different, but again, very similar, right? So instead of 4, you have 6. What about in 3D, right? We could have, if you're working on let's say an atmospheric code, okay? If you're using, let's say, the Department of Energy's in the US, E3SM. What they do, right, is they want to carve up the space of Earth, right? So this could be a mesh on Earth. And they do very regular patterns in order to be consistent and have basically known communication patterns, right? It's very simple. So here, right, this is the surface of a sphere split up into regular triangles, right? But you can imagine if this is a 3D, like if you're looking at an atmospheric code, they have columns, right, where they actually have prisms, right? So you have triangles on the ends, and then each of the triangles are connected by a quadrilateral face. I can't say that. Right, and they extrude off of into 3D space, and then you can have like water vapor, for example, as your variable, as your solve, okay? So you can make structured meshes, regular communication patterns, right, out of all types. So I have pyramids and tets, hexes are pretty easy, But you can have even crazier elements, right? But it's a known communication pattern, right? So you can construct lots of fun stuff. For annoying, if you really want to. Okay? So now, partitioning, right? So partitioning, what is the big challenge here? You have this mesh, right? The whole goal of using MPI is I have a problem that is generally too expensive or takes too long to solve on a single MPI or a single core, right? And you want to use more computational hardware to accelerate your program, right? So we have to split up, partition our problem, right? So for Cartesian, this is pretty straightforward, right? So our goal, right, is to load balance where we hope to split up the problem to use the same number of elements on each MPI rank, for example, or processing element, because we want to have basically the same amount of work per core that can run in parallel, and we're not waiting, right? So here, if we had 4, this one's pretty easy, right? We just chop it all up, and then each processing element has 9 pieces of information to work on, right? Pretty straightforward, right? How about this one? Same idea. If we have 3 MPI ranks, we can, again, partition this structured mesh. It's a little bit more complicated, right? But they're essentially contiguous chunks of elements, right? And they each have the same number of elements. So if the amount of work is the same, then this should be fairly scalable, right? Okay, how about this one? This one's a little less trivial. How might we partition this one up? Any takers? How would you do this? Yes, you're counting. I'm going to put you on the spot. You could, yeah. That's one way. Or we could, well, as a caveat, we could just do the original same one. But what's wrong with that one? What's the load and balance, right? So we know that ranks 0, 1, and 3 have 9 elements of work, right? 9 pieces of information to solve. But process 2 only has 5, right? So we have a load imbalance, right? So pros, right? That was easy. We just used our original scheme, but we just ignored the holes in the mesh. And of course, cons are the load imbalance, right? Cyclic processing. What we could do with this one is we can literally start at the top left, say, okay, process 0, you get the first one. Process 1, you get the next one, right? And so we're seeing 0, 1, 2, 3, 0, 1, loop all the way back, 2, 3, right? So it's just a cyclic pattern. But what's wrong with, what's good about this one? It's easy. It's easy. Nothing. You're pretty much right. You're like, this is garbage. I get terrible performance, right? But on the face of it, it's easy in terms of the partitioning scheme, right? You're just like, oh, okay, just give me all the indexes, loop it out. It's round robin, right? So this would be a round robin scheme, like bland, right? One element per core and loop around and go. But as already alluded to, there's nothing good about this, okay? And that's because the data is really split up. So now, because, right, who does partition 0 have to talk to for this element? Now it's going to have to talk to 2 other MPI ranks, for example, right? The data is not local, and so that's very expensive because computing is about data movement, basically everything for performance, okay? You want to localize your data and only work on what you have in your RAM now and try to use it as much as you can before you discard it. Or in terms of communications, this one, you have to send a whole bunch of messages in order to do the computation, right? Okay? A little bit more advanced. What's good about what's good about this one? Yes. Correct. So we're getting back to they all have the same amount of work, and most of the elements are consecutive, right? So again, contiguous, right? So we're reducing the amount of communication in order to do the calculations, right? Well, what's a con to this one, maybe? Yes. Well, yeah. It's just more complex, right? In order to like do this partitioning scheme, right? So in order to do this partitioning, it takes more time to like figure out how we do that. Unfortunately, right, this is just a Cartesian, but in order to really do this, we would have to use a graph partitioner, right? And luckily, there are codes that are available to do that. And at the very end, we'll actually do one, and I'll give you an example so you actually could do this. But it is more complex, and generally, MPI does not care. They're like, hey, you have to tell me how to partition this. I'm not going to do it for you most of the time, okay? But we'll get to that a little bit. Okay, so it's a little more complex, right? So back to structured meshes. What are the pros? Data locality is fantastic. Communication patterns are known, right? It's very consistent. You know what's coming next, in a sense, right? But what are the cons? It's simply a kind of a trivial, topology in a sense. So the real world is much more complex, right? So from my wind farm simulations, that is not trivial, right? In order to do Cartesian. There are methods that do this, but we'll get back to it, okay? So how do we partition octrees? Hey, we heard about this today in the opening keynote lecture. The professor talked about Morton octree adaptive, what was he doing? He was doing, I forget. Anyways, so the dark green, what it does, take a Cartesian mesh, and you're like, okay, I want to adapt. Meaning I want to take one of these elements, I'm going to split it into 4, okay? But if you think of it as a binary tree where you start with one element, and then that gets split into 4, and then those children get split into 4, and then you actually connect all the children, and that's called actually Morton code ordering. So it actually, this morning, we actually heard a little bit about this. And so there's easier ways to partition these like green ones that aren't quite Cartesian. And how do we partition fully unstructured? Well, we have to go back to graph partitioners. What if we're doing even crazier stuff? What if we have unstructured meshes that are dynamically changing in time? Right? Then the graph partitioner also, how long does it take to graph partition? That can be a lot of, the wall clock time can explode, right? So medicines actually can be expensive, right? So is there ways we could combine these things, right? Just from that. So, okay, in the end, partitioning is hard, period. If you didn't get it, ready? Hard, period. Okay? In general, it's up to you. But even though it's an MPI lecture, learning from last year's feedback, I'm going to actually give you some potential solutions on actually partitioning hard stuff. Okay, potential options. Cartesian, we're going to use actually an MPI thing. It's called DIMS create, which can take a fairly straightforward, okay, my Cartesian grid has this many nodes. Give me a partition on, say, like 6 ranks or something, and it'll split it up for you if it can. Okay, octree, that's the adaptive green mesh thing. Well, we can use Morton code orderings, but that's an advanced topic. It's actually pretty trivial in terms of cutting up the graphs, but if you have questions, you can ask me later. And then finally, on structured meshes, we can use metis or parallel metis, par metis. But we'll actually see this in section 5, and the hands-on, you can actually run metis, have a real working demo, so you can take home and make your fun graphs and partition them up. Okay, virtual topologies, what are they and why do we have them? Okay, so a virtual topology is simply an arrangement of MPI processes, and why is it useful? One, we can make, for example, in a Cartesian topology, we know the communication patterns are regular. So why don't we just tell MPI about it, and then we can make the communications ourselves, like one MPI send instead of sending 4, to simplify things, okay? Second, let's see here. Right, oh, I guess I was talking about that. On the previous one, we can construct the actual topologies easily in MPI by using what's called a cart shift. And then, right, as alluded to, we don't actually need any of this stuff, but it can be useful and help for performance, right? And simplifying the code itself. If you do a little extra work up front, you can get rewards on the back end. Okay, all right. I think in terms of time, I'm going to skip over this. There's a whole checklist of factors to consider, like, you know, hardware, how many, like, NUMA regions, right? So you have non-uniform memory accesses and all this stuff. I'll defer to the slide deck if you guys are curious about this, okay? So let's skip over that. Again, whole goal making virtual topologies is to hopefully get better performance. And the reason why is if the implementation is good of the MPI standard, you can ask it to reorder the ranks and take advantage of the underlying hardware in order to map your problem to better localize the communications. Now, do they really do it? Okay, reality versus a perfect imaginary, perfect world, right? But we just want to give you tools that you can try to see if it'll work. Okay? All right, we have our simple Cartesian topology, and our goal is to make what's called a communicator, right? So it's a communicator. Communicator is like our world of who we're going to talk to, right? So if each one of you is a processing element, inside of COM world, you all have a unique rank ID, 0 through 45 or so, right? But for example, if I know or you know you're only going to communicate with people at your table, it might be beneficial just to make your own local communicator a sub-communicator, right? So that way, if you say, oh, MPI all reduce on my tiny sub-communicator, I only communicate with the people I need to talk to, instead of everyone, right? We can do the same thing with making a virtual topology, a Cartesian one, so we know it has embedded, oh, because this is a Cartesian topology, I only have to talk to my 4 neighbors, for example, or in 3D, 6 neighbors. Okay. All right, so how do we actually make a Cartesian topology communicator? So again, similar, we pass in our old communicator, which could be like MPI COM world, or if you have your own already communicator that you want to build out of it. Then you tell it what is the dimensions of your Cartesian grid. So in today's example, we have a 2D problem that is a Poisson equation, which is like heat distribution. Or if you want, you could think, oh, I want to do an edge detection algorithm or something on an image, right? So you tell it dims, and then the actual dims, you have to say, okay, a part of my grid, I have, let's see here. This array is going to be, if I have a 2D array, then NDims is size 2, the number of entries is 2, but then I can specify or get out what the dimensions, how it gets partitioned up. Okay, or actually I have to pass that in. We didn't do the partitioning yet, sorry. So we pass in the partitioning, because we did it ourselves, or we asked MPI to do it, and then you tell it if it's periodic, right? Do we talk, if we go back to here, right? Try to be fancy, right? So here, this is a periodic function, right? So at rank 0, it's going to loop all the way back around and talk to rank 3, right? So we can pass that information around, and then when we ask who's my neighbor, and I run off the boundary, then it's easy to get, oh, okay, MPI is going to tell me it's 3, which is nice. Okay, so we can tell MPI that stuff. Okay, now the one flag, right? The hope and goal is to get better performance, and that's through this reorder flag, which may, depending on the implementation, may or may not actually reorder the ranks within this communicator. And then finally, you get your brand new communicator, right? Okay, so how do we actually create the DIMMs, right? How do we actually create DIMMs that goes into that previous function, right? This one. So this is an input in, but we can use MPI to actually make DIMMs and get this out. So how do we do that? This also partitions the grid, right? If I wasn't clear. So we tell it the number of nodes in the whole grid, number of dimensions, right? 2D, 3D, ND. You can even make it 0D one, does nothing. So that's fun. But it's there. It can do n-dimensional partitioning of Cartesian grids, okay? Let me clear this, hopefully. Oh, word. What is it doing? Oh, no. There we go. Warning. All right, so DIMMs is an output, right? But it's actually, in this context, if you're in Fortran, we say it's an in-out. So you can actually pre-fill DIMMs with some non-zero entries, and that tells MPI, hey, I want this entry to be, as such. So if I erase this, right? So if we look at, for example, we had DIMMs before and they both had zeros, this tells MPI, hey, you're free to change these indices. And then let's suppose we have a Cartesian grid with 6 elements. I want to partition it to be in 2 dimensions. What do I get back for the DIMMs? It's going to tell me, hey, you should partition this using a 3 by 2 splitting, in a sense, right? Down here, we see 0, 0 again. MPI, please feel free to change any of these DIMMs. Let's partition a mesh that is 7 entries in 2 dimensions. Well, that doesn't work very well, right? It's prime number. So it's actually going to only split it to 7 by 1, right? Sense? Okay. Down here, we're going to fix the y direction, right? This one, to be 3. We're going to pass in 6 nodes. So it better at least have a 3 in there if it can. And then how is it going to split up? So 2 times 3 times 1 gives me 6. So it's going to spit that partitioning of a Cartesian mesh form. Okay. Lastly, if you try to do something not smart, right? We ask for 3 and y, but we give it 7. We can't partition, right? A 7 node Cartesian map in 3 dimensions with a 3, right? It's going to give us an error. So when you call these functions, right, you get a status back. That's what this return value is, int. So in theory, you should be checking what that return value is to see if you screwed it up, right? Good, safe, defensive programming. And if you want, you can jam that to a, if debug mode, check the type and assert that it's not garbage, right? So, okay. Now, why is this useful? You built your brand new communicator on a Cartesian topology. It's like, great. Okay. What you can do is you could say, hey, I'm going to pass in some coordinates. Oop, let me see here. I want to pass in some coordinates for, say, rank 6, right, where the coordinates themselves are 1, 2, right? So we have 1, 2. And what it does, it spits back its rank, right? So it's really going to spit back 6, right? So you could be sitting on some rank, or you could be querying, right? You pass in the coordinates of, I'm on this part of the Cartesian topology, give me the rank. There's also, you can guess what the next thing is. What's the next thing? Yes. The other way, yes. Yes. Okay, so we pass in coordinates, right? Or, sorry, we pass in the rank and the dimensions, and it's going to spit back the coordinates, right? So just the opposite. Pretty straightforward, right? Okay, this is the secret sauce of Cartesian topologies. And so this is where the power comes in. You've now figured out your Cartesian topology. You told it how it's partitioned, right, in terms of those earlier functions. And now we want to ask, hey, if I ask I have the ability to ask or query MPI, say I am rank 6, and if I say if I shift +1, and then I say displacement, as we'll see, is which direction are we going to shift in the x direction, right? That dim, which dim are we going to shift? If we say shift +1 in the, direction, x direction, so 0 with index dim, and then displacement +1, I can ask, who am I sending to? Who am I receiving from, right? So if I imagine I'm sending like this, positive, okay? Then I can get these ranks, which is where the power comes in, okay? So cart shift for the hands-on exercise is this fun routine, right, where we have to say what's the coordinate index, how many if we do a positive shift or a negative shift, and you can put in any value basically. Okay, now there's something last year I totally screwed up on this, okay? If I am on this grid, if I say shift in the y dimension, let's start with x. X dimension +1, right? So x direction +1, I will send to 2, and I'll receive from 0, right? Let's suppose I'm at 6, and I say in the y direction +1. Who do I send to? Do I send up or do I send down? So positive direction, I'm sending in the positive direction. Which one is the positive one? This one or this one? Down, okay? The reason why is lexicographic ordering is built into the assumption, okay? Now, what is that? Okay, lexicographic ordering. This is a stack of books, and if you're like in the, not in Iran, right? You read on the page, right? You open the page, and when you start reading, you start in the top left, and you move across in the x direction, positive, so you're going from left to right. Then the y direction says I move down the page is positive, right? I'm moving down the page. That's why it's a positive. Shift is down. +1, and the y direction is down. And then z is into, you're going to turn the page, right? We're moving through the pages. Okay? Any questions? Yes? If, yeah. Mm-hmm. So you will get what's called MPI proc null. And if you pass that into a send function, it knows how to handle it. So you're totally safe. You don't have to check, is this MPI proc null? You're fine. You can actually pass it in. It's like, oh, I know what to do with this. It just returns. So it's clever in that way. Yeah.
If there's, if there's like a status code where you can have a physical boundary and set that handle.
I suppose, yeah. So I guess in this example, right, where when I did this in my real code, which you'll see, I'm not going to show you. It's basically these functions, right? But it was a physical boundary of my computational fluid domain, right? It was like, okay, it's a flat plate, that's ground. I did know, because I have to call cart shift in a direction, right? So if I know I'm shifting in a positive y, and I know I was supposed to send to down, but I got a proc null, I knew it was a y boundary. Right, so I'm using the context of the call to make those choices. Okay. Yeah, last year I was telling everyone the back way because I was thinking of like matrices, right? Yeah, totally wrong. Lexicographic ordering will save you. Okay, here it is. This is what I really did on Mira at what was called, there's another program in the United States called the Argonne Training Program for Extreme Scale Computing. It's a similar HPC workshop, but it's 2 weeks of way more intense HPC training, but they give you access to their resources. So for example, what was nice during this program, I took my software, which is a discontinuous Galerkin code, on a Cartesian mesh. Here I'm actually showing adaptive mesh refinement, but this was a purely Cartesian one. Nothing was adapting. And they give you total priority on the queue, so they put my queue score to like 10 million. So I jumped everyone and ran the entire supercomputer. So I'm sorry, all the DOE researchers, but I was able to make this scaling, right? So on the, I basically did this periodic problem with a turbulent flow, which is called the Taylor-Green vortex, if you're really curious. It's a canonical test problem. And then I actually scaled it up. And the unique thing about this computer, Mira, it's now decommissioned. It was pretty awesome. Had a great communication network topology. It was really fast. But it also had, per physical core, it had 2 mathematical, arithmetic mathematical units. Okay? So that means I could actually run 2 MPI ranks per core and get a speed up. Normally, these days, we don't do that all that much. But by doing that, so what's shown in blue is the strong scaling. You can barely see it here. It's like perfect because I ran a problem that was like 100 billion elements, right? A crazy huge problem on over 1 million ranks. But then so you're getting like 95% strong scaling. The problem was too big. I didn't actually learn anything useful out of it, right? But it goes to show that if the implementation is good and correct and you use it, you can get really good performance if you use it correctly, okay? And the time to solution was actually 64% faster by using the 2 cores on a single core, or a single MPI rank. Okay, hands-on activity. I'm like super fast today. This is the last exercise of today. So you can either go back to derived data types and find all the bugs that I put in there, which there are a few, and thank you if you found some, like sending to yourself if you're rank 0, and yeah. So there are a few bugs in the previous one, but for the next one, we're gonna actually do this problem, okay? This is a solution. This is gonna be a 2-dimensional Poisson problem solved with a finite difference stencil, right, in 2 dimensions, right? So if you get the correct answer, this is like a problem that's been partitioned over 8 ranks, so 4 by 2. And then we have 3 heat sources, and over time, these heat sources diffuse out, and you can actually see these. These files are written out to bitmaps inside of the directory, so when you get it working, you can check to see if you get the right answer, plus there's like a final heat score in a sense, okay? So let me shift over to the other one, and we'll do some explanation of the problem and see the code, and then I'll let you guys figure out how to do this cart shift and all this stuff and run it. Okay, any questions so far? Okay. So back to the exercises, right? So in exercises, there's exercises.2, Cartesian topology. Do not go to the Fortran because I did not implement it. Is there actually any Fortran programmers? 2, 3. Hey, time to put on some adult pants and learn C. No, I'm kidding. Oh, I'm kidding. No. In reality, my real research code, I literally write all of my kernel functions, my mathematics, which are tensor contractions for multi-dimensions in Fortran. And I actually have everything orchestrated in C++, and I call Fortran functions. Because of the tensor indexing is way nicer than having to do it over in C. So because it has reshaping automatically in Fortran, it's super awesome. Because I do like contractions on like the third index of this multi-dimensional array. Like crazy weird stuff. And to do it over in C, you actually have to do all the like, oh, how many am I skipping index Y, and do actually the calculation yourself. But Fortran natively does that, and it's fast at doing that. So it's been really hard for me to actually get the performance otherwise. Yeah. So the reason why I don't use pure Fortran is on top of this, I actually have it linked to GPU code. So I have C++ on the front end, which has, I've overridden the memory pointers to be either CPU pointers or GPU memory, and then basically with C++, right? And then I can pass it. Yeah, so that's why. So I didn't want to do the hoopla of Fortran and pointer interfaces and all that stuff, okay? All right, so back to this. Here's the problem, Poisson's equation. Bring you back to your good old PDEs, right? So we have nabla. This is a, let's actually do some math, right? So we have, do I have it here? No, I don't. Okay. So what is this, right? So this is like dx squared. Sorry. No, just kidding. I have not taught math in a hot minute. Okay, so du dx, right? And then you're going to do a second derivative, right? So d dx on top of that, right? So we have del squared u dx squared plus d del squared u of, oh my word, dy squared equals f, okay? Anyways, no need to worry about that. You guys aren't going to be programming a bunch of, finite difference stencils. That's already in there. The important thing is we just want to look at how do we construct all of this fun Cartesian topology stuff, okay? So, regular neighbors, great for, we have a 2D problem. And now we have this giant mesh, okay? And we're going to partition it, for example, in just what I'm showing here, into, say, 3x3 grid, right? Cartesian topology, right? So with this, right, then I have, when I do this partitioning, it's a little difficult. So we have variables in the code called Rx and Ry. And those are the rank IDs, in a sense, in that direction, right? So here, the rank coordinates is 0, 0, and the value of the x1 is Rx. So like here, right, that's what I'm indicating. So if I want to go to a rank, I go to Rx, Ry, right? So try to pigeon scratch this, Ry by Rx. Right, so that's the if we recall, those are those cart coordinates, right? And we're going to use cart coordinates to get out ranks, and then from there we'll figure out our neighbors with the shifts. So your job in the exercise will be to compute Rx and Ry, use cart shift, and then actually do I think there's a communication in there. I don't know if I have that still in there, or if it's you just pass the communicator in. We'll see. You guys will figure it out on the fly. And then do the calculation and see if you get the right answer. Okay. So a little bit more animation. So what does this look like? So on these partition boundaries almost, right? What we want to do is on the green, right, this, oh my word. This is on a partition boundary, and on this rank inside the red, right, that is my valid cell that belongs to this rank, 1, 1. Now, I need the neighbors that are shown in yellow to finish my calculation, right? Because when I do this finite difference stencil, I need my 2 nearest neighbors, and then it's basically an average to get here, right? So that's why on this green one, I will need this one here above me in yellow, which will be, I call them ghosts, ghost elements. And then I also need the one below it, but that's local inside the grid, okay? Erase all that. Okay, and so if I take this, now inside of the actual code, we actually over-allocate. Now, does this look familiar? Did I not show you this a bunch of times, right? So the dimensions of the internal is bx, right? So there are bx green elements across the top in the x direction, but we actually save a grid that is bx plus 2, right? So that's our 2D array. And then also ry, so it's really by plus 2, right? So this grid, bx plus 2 by by plus 2. Okay? And so if you were to actually plot this thing, you're going to have a heat source planted throughout the domain. Okay? So it's basically these spikes of heat. And they're located at there's 3 of them randomly placed. Okay? If you really want, inside the run script, you can set the number of heat sources and all this fun stuff, but it's automatically scripted for you, so you don't have to worry about it. But they're heat spikes, right? And so as this calculation runs, this Poisson equation, it's basically how are the physics governing heat? And it's diffusing out. So if we looked at the spike over time, even though it's not traversing, it's just diffusing right out. And so that's why you see, like on the animation before, we saw it like a spike and then, so that's what's going to happen, okay? Okay. I said you have 20 minutes. You more like have like 40 minutes. So we're going to basically run through this. I'll let you guys run through this example. We can pull open the code shortly. And then we'll look at it and look at the 2D or the to-dos inside of there. Okay? Question? Sorry. It's not periodic. But recall, you're going to get, if you're going to query, right, you're going to ask, when you do a shift, you're going to fill in, hey, who's my north, south, east, west? So you'll see in the code there are variables northwest, north, east, southwest. But when you're on a boundary here, and I ask, who is my east neighbor, it's going to give me MPI proc null, which gets stored. And because it's going to get passed into the MPI send or receive function, MPI automatically knows what to do with it. It ignores it. I think there are boundary conditions built into this program that handle that, right? It actually checks MPI proc null, like you were talking about earlier. Okay? Any questions? I know it's been a long day. You guys are doing great. Okay, pull open the code. Let's see what happens. Oh, another fancy thing. This thing is disappearing. And it swipes back and forth. And in 20 minutes, it'll stop. Ah, yes. Little details of the stupid PowerPoint.